Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to introduce Mahesh, who is visiting from University of Waterloo, and for today, and we'll look forward to discuss access control policies and analysis of these hear what he has to say in the talk and discuss over the day. Thank you.
Thanks, Nikolai. Thank you for showing up, and to whoever is watching as well. Okay, so what I'm going to do is I'm going to talk about 3 problems. Each of them has an acronym. I'll first explain what they are. The first couple I've worked on with my grad student, Nima, at Waterloo, and the other one is Karthik's work with some collaborators. Okay, so just to give some context, so those are the 3 problems. Just to give some context, what is access control? Well, we think of a setting where we have a user that tries to access a resource. We typically qualify the access with what the kind of access, in this case read. But that's not exactly how it works in computer systems, of course, because we think of an intermediary, like a processor or something that actually does the access. So the user instantiates an agent who does the access. That becomes a little bit important in the context of one of the problems that I'll discuss. Now, we typically don't think of every user being able to access everything. So conceptually, we think of an intermediary called a reference monitor that mediates the access and allows or disallows. The question is, how does the reference monitor make its decisions? And the answer is it has access to a database called authorizations, and it consults the database and says yes or no. This process is called access enforcement. Now, the authorizations can change, and that process is called administration. The simplest model for administration is that we have a super user that goes and changes the authorizations. For example, Alice is allowed to read the file today, but not, maybe tomorrow because she's no longer an employee. That's the simplest model, where we have a trusted super user that makes all the changes, but that doesn't scale. So we usually have this, we have this notion of delegation, where the trusted super user delegates some power over changing the policies to a partially trusted administrator, and that's called delegation. So this gives somewhat of a broad context in which I can pose the 3 problems that I'm going to talk about. Just in the interest of having a specific syntax for authorizations, a specific language, I'll adopt a role-based access control. What is it? Well, it's just rather than a user such as Bob or Alice directly getting a permission, which is at the bottom, I just give them some names such as budget, hire, and things like that. Rather than each of them getting permissions directly, we have an indirection that we call a role. In this example, finance, human resources, and so on. Now, if you are familiar with the RBAC, you'll notice that in this example, I don't show a role hierarchy, and there's a reason for it. It turns out that in the context that we discuss, the role hierarchy doesn't add any complexity. Okay, so first let me talk about the user authorization query problem, the first of my problems, and the context. That is the kind of the context in which the problem is posed, which is the access enforcement part. So here's the issue. The way things are defined in RBAC and also in some real systems is, if a user wants to exercise permissions, she instantiates what we'll call a session. So if you download the Oracle database, for example, this is exactly how it works. What is a session? Well, a session is a set of roles. Now, the immediate question that arises is, if I'm a user, why don't I just establish a session and that has all the permissions to which I'm authorized? The reason a user does not want to do that is to adhere to the principle of least privilege. So the thing is, a user should only establish a session which has the permissions that she really needs to get the job done, right? So for example, if Alice wants to activate a session with the permission pay, presumably she would activate only human resources or purchasing, right? She shouldn't go and grab all the permissions that she has for the session. So in this context, we get a natural problem. So here I'll pose it as a decision problem. So given an RBAC policy for a user, rho, and a subset of a permissions P, and let's say an integer k, does there exist a set of k roles that yields the set P? And just by way of notation, I might use this notation of a language rather than this input-output thing. Of course, the correspondence is straightforward. So language is a set of tuples, and each component of the tuple we can think of as an input to the decision problem. In this case, the policy, the set of permissions, and the k. Now, it turns out that deciding this language, this decision problem is intractable. This was shown back in 2006. Now, the thing is that, okay, why do I care about the decision problem? Well, there's an optimization version that's kind of a natural correspondence, and the optimization version, of course, we don't have the k, and we just ask, okay, this user wants to establish a session with these permissions. What is the minimum size set of roles that she needs? And of course, given this NP completeness result for the decision version, we know that the optimization version is NP hard. So there's a natural correspondence between the two. Now there's another version of this UAQ problem, which I'll call UAQ-P, the focus on permissions. So what people observed is, well, I don't know how much we should care about a minimum set of roles that yields a set of permissions. Here's another kind of take on this problem. We notice, for example, in this example, so I've eliminated the users because we're focused on a single user. So in this case, this refers to Alice from the earlier pictures, that if she wants a session with the permission pay, she has to make do with some extra permissions in the session, right? Because there is no role that yields just that permission, or no set of roles. So this is a practical issue. So she may have to deal with some extra permissions in the session, and specifically it may be impossible to get an exact set of permissions. So in practice, maybe we want to allow some slack. Sure.
The finance human resource purchasing is the role, right?
Yes.
And the bottom layer is the permission.
Yes.
Okay.
So the NP hardness is
This one?
reduction is that easy? And
Yes,
we
it's very
set
easy.
and we put the
Or actually from set cover, it's even easier.
set cover.
Right. So basically we're looking for a set of roles that covers some permissions. Right? So this is exactly like set cover. Right. So I used to have a line in the slide where I said it's straightforward reduction and set cover. I just removed it because it seemed to be. So this version, what we do is we allow some slack permissions. So don't just, as input, we don't just specify an exact set of permissions. We say, well, these are the permissions we absolutely need. So here's a new version.
So by that you mean that Alice wants to pay, but then she also gets permission for the invoice.
Yes. Right. So if she, for example, activates purchasing, then she's going to end up with the invoice thing, because she cannot exactly get the pay thing. Yeah, that's exactly what I mean. So here's a new problem or language. We have the RBAC policy rho. We have a lower bound set of permissions, and then we have an upper bound set of permissions. So the difference between the upper bound and the lower bound, presumably the upper bound is a superset of lower bound. The difference between them is exactly the slack that Alice is willing to tolerate. And now we have the K, because what she wants to say is, for example, I want as few extra permissions from PUB minus PLB. She could also say, now there's a maximization version also that people have considered, which is where she says that, well, give me as many extra permissions as possible, just to make it easier to get my job done, right? Now this version is also intractable. It's a NP complete specifically.
Is anybody interested in solving this in practice? Because this is a max problem.
Right. So in practice, these, I can tell you that from what I know, database, so specifically Oracle, they don't implement this, but they have exactly this, meaning they have the notion of a session, they have the notion of roles and things like that. So it may be meaningful to put it in there. But I haven't talked to anybody at Oracle.
Because it seems to be like a directly, you have hard constraints as the lower bound, and then the set difference of bound.
Right.
self-constraint and you minimize
Right.
the dependency
Yes. So it's very, yeah. So of course the optimization version is we drop the k and then we want to minimize or maximize the extra permission. So this is what the word. Okay, so we came along and then we decided to, well, somebody else actually combined the two. Now the only other, so the combination is that we, combine these two optimization problems. Now it turns out that in the literature, and this comes from the NIST RBAC standard, people also consider an additional input, which is a set of what I'll call the separation of duty constraints. Each of these constraints looks like this. It's a pair, which is a set of roles and an integer t. And the meaning, the semantics of that two tuple is that a user is allowed to activate at most t minus 1 roles from that set R. So the idea here is some kind of mutual exclusion, right? So we talked about the principle of least privilege earlier. The intent behind this kind of constraint is to force the user to adhere to some kind of least privilege. Basically saying that, well, if you activate these two roles, then you cannot activate this role as well in the same session. That is the intent of this kind of constraint. So the general problem is like this, right? You have this policy row, you have the lower bound set of permissions, you have the upper bound set, and then you have these two integers, k subscript r and k subscript p, which capture the optimization objectives, and you have these constraints that have to be met. And the question is whether there exists a session that satisfies these constraints. So from the standpoint of computational complexity, we have a lower bound because the special cases we know are NP complete. So that in general we know that UAQ is NP hard. We also have an upper bound. It turns out the upper bound doesn't change. Yeah.
I'm more interested in the background of this assumption. So could you give me
This one?
Now the previous problem statement?
Okay.
You mean that there are some roles which mutually exclusive?
Oh, that is this one.
Yeah, this one.
Right. So the simplest case is that you give me a set of roles R, let's say the 5 roles, and the T is 2. And the meaning of that is that at most 1 role from those 5 roles is allowed to be activated in a session.
Okay. So I mean, in practice, there any case like this? So when we have this semantics?
So this is in the NIST RBAC standard. So if you ask me about a real system, I cannot, I can tell you.
Okay, you mean in standard we have this, for example, term or something have this requirements.
Yes.
But, okay.
Right. So I can't give you a concrete system,
Okay.
operating system or database system. All I can tell you, I don't know if, for example, to use the earlier example of Oracle, I don't know if they've implemented this in the thing. I haven't checked that.
Okay.
But it is in the NIST standard. So one of the problems that I worked on earlier, actually I was still a PhD with my supervisor, was does this kind of constraint make sense?
Okay.
So, the fact that they put in a standard, we were asking, does it even make sense to have this kind of constraint, right? And the answer was yes. Like if you take a more abstract notion of separation of duty, it turns out that these constraints do make sense. But nobody had looked at it in the past anyway.
KR and KP.
So those are the kind of capture the optimization objectives, because I want so many roles. I want a session with KR roles and KP extra permissions.
Okay.
Let's say at most KR roles. So they're exactly from the earlier K. So for this K is KP because it's the extra permissions,
Okay.
and this K is the KR because this is the number of roles, right? So it's a 2-dimensional optimization problem.
Okay. And do they have, so you get a parental problem?
Yeah, so that's what I was going to say here. So I'll talk about that in a second. Right, so you do get a Pareto fund. Okay, so in terms of computational complexity, it doesn't change from the special cases. So the upper bound is the same. Of course, we have a lower bound. Now the optimization version, so the optimization objectives are the number of roles and the number of extra permissions. And I just want to point out something that we expect, which is natural for many of these problems that are NP complete, is that given an oracle for the decision version, we have a polynomial time Turing reduction from the optimization version to the decision version, right? So all we do is a two-dimensional binary search on these two integers, and then we get the optimal. But yeah, you are right. So we can have incomparable solutions. So this is a simple example. So if the lower bound set is budget and pay, and the upper bound set, which is a superset, includes the hire and layoff, and we have no constraints, then we have two optimal solutions depending on our optimization objective. So if we want to minimize the number of roles, then we should pick human resources, but that yields 2 extra permissions, right? But if we want to minimize the number of extra permissions, then we should pick those 2 roles. But that gives us 2 roles. So yeah, so we end up with the Pareto front. And so what we say in the paper is that one way is that we could explore the Pareto front, or we could just prioritize one of those objectives over the other. Saying it doesn't.
So if you select purchasing,
right,
you get invoice.
Right.
And invoice is not in the upper bound. It does.
Oh, you're right. So I should have put the invoice in the upper bound. I'm sorry. It's a bug in the slide.
Okay.
Thanks for pointing that. Yeah, that's a good point.
So
my mistake.
Right. So the semantics is you must have. You cannot have anything that's outside.
Correct. So when I talk about the encoding a set, that comes up. Yeah. So you cannot have anything. Yeah. So that's a bug in the slide. Sorry about it. Okay. So what we did is, okay, how do we mitigate this intractability? So we, I take a computational complexity kind of view, which is, okay, so we can use a constraint solver that is complete for NP, or we can look to approximation theory because we have an optimization problem, or we can look at the theory of fixed parameter tractability. So let me look at the approximation theory. So of course in approximation theory, the interesting thing is that what the theory does is shift the focus from time efficiencies to something called the approximation ratio, which is what in the worst case. So the point is that, okay, here's an efficient algorithm for this problem. So assuming that P is not equal to NP, we know that there has to be a trade-off somewhere. And the trade-off is what in the worst case, how bad could it be in terms of the solution compared to the optimal solution. So if we're talking about a minimization problem, we expect that in the worst case, the approximation algorithm returns a result that is not the minimum. But how bad could it be if I take the result of the approximation algorithm and divide it by the minimum for that instance, right? So we expect 2 kinds of results for an algorithm. 2 kinds of results. One I'll call a positive result is I present an algorithm to you and I prove to you that in the worst case it achieves a certain approximation ratio. The other is the main thing behind the approximation theory, which is that negative results, which is to show that a certain approximation ratio is the best that you can hope for. So here's an example of a result that we have. So the optimization version of the role thing, which is UAQ-R opt, if it has a solution, then we don't expect to be able to efficiently approximate it within that kind of approximation ratio, right? So if you look at it closely, it's basically a horrible approximation ratio because it's a polynomial in the size of the input. So this is pretty much the strongest negative result you can have from the standpoint of approximation. Now, why do we have the qualification assuming it has a solution? Well, it's because of these constraints, because the constraints may result in no solution existing. So, in which case we have a pure decision kind of problem. So first we have to address a pure decision version problem, which is, does the solution even exist? And okay, fine. Even if it exists, even if I tell you, given an instance that it exists, you don't expect to be able to efficiently approximate it within a polynomial factor.
So square root of n, cube root of n.
That would not exist, right? Because, yeah.
Because of that.
Yes. So this is the strongest negative result, to my understanding, that we can get from approximation theory. Because chromatic number is efficiently approximable within cube root of n or something like that, the graph coloring thing.
Okay.
Right? But vertex cover is efficiently approximable within a constant factor. So there's a very simple algorithm which is within a factor of 2. Like I'll end up with a vertex cover that has more double the size. But actually there's another algorithm that I think
but
actually...
you said cover already, like, or you just trivially from set cover, you say set cover body already has a known constant, is like log n.
Right. So set cover is a different class because it's log n, and you can actually show that the log n is a tight bound.
Yeah.
Right. It's both the lower and the upper bound. Yeah. So the thing is, how do we prove something like this? Well, there's a kind of the user-friendly way is, at least for me, is to for those of us that are familiar with the NP hardness reductions, the CARP reductions, is there's a different kind of reduction called a gap introducing reduction. And the way it works is that we reduce SAT in a way that introduces this gap alpha, which is the approximation ratio. And this immediately implies that it's NP hard to approximate within better than alpha. Now for the permission version, the CARP reduction from set cover to UAQ-P, the decision problem, can be easily adapted to a gap preserving reduction, which is that, and because we know that for set cover we have a gap introducing reduction from SAT that shows that you cannot approximate in better than log n, we know immediately that UAQ-P opt cannot be approximated within better than log n. Now the thing to point out is that this is only a lower bound, right? So we don't have an upper bound for UAQ opt, UAQ-P opt. So it's just saying that, so this is a weak inapproximability result, and we don't have a better result, like the lower bound could be worse. Okay, now fixed parameter tractability, I'm going to be a little bit informal. This, the theory is much richer than what I suggest here. So if you're familiar with it, forgive me for it. So the only question that I'm going to ask is the problem in P if we assume that some parameter is bounded in size? What is a parameter? Well, a natural parameter may be an input, something input. So for example, it may make sense to bound the number of roles in the policy, or maybe the permissions, these lower and upper bound sets, because we are dealing with the least privilege. So, let's say that Alice, we assume that every user wants to activate sessions that only have 5 permissions, for example, something like that. If it makes sense to make those assumptions, the question is, does the complexity change? Because then maybe we have a different approach to deal with it. So here's an example of result. So of course we assume P is not equal to NP. Then basically we have a necessary condition for UAQ-P to be intractable, which is that these 3 parameters have to be unbounded. So if any of them is bounded, then we know that UAQ-P is in P. And this is slightly overstated because if PLB is unbounded, then we know that PUB is unbounded because the PUB is a superset of PLB, right? Okay, so this is a one-sided implication. It's not an if and only if. Specifically, we have this case that if only these are unbounded, then we have an algorithm that's in P. Of course, it's exponential time if you assume any of them is unbounded. We actually have a slightly better algorithm if we can make an additional assumption. So here we are assuming that PUB is bounded. So from the previous theorem, we already know that the problem is in P. However, if we can make this additional assumption, so I can argue for it in practice, which is that the number of roles that's a solution is at most the upper bound set. So what is the justification for this? The justification for this is that, well, to get a permission, I need at most 1 role. Right? It doesn't make sense to have 2 roles to get a permission. Right? So that's the justification for this. So if we assume this, we get a more efficient algorithm. That's the point of this. So these are examples of some results from assuming some boundedness. So that was the second way that we approach.
The way that you informally describe the low-based axis,
right.
You only need 1
Role
for
a permission. Right. But the thing is that if you think of a maximization version, I don't know if that makes sense. If you're trying to maximize the number of roles in a session, I don't know why anybody would want to do that, then that doesn't make sense. That's the only thing. But what we're saying is because the maximization version does not make sense, that assumption may be reasonable.
But are there any twists to the role-based world where you need two roles to get a certain equation?
So that's a very good question. The short answer is no. Nobody has explored semantics for RBAC that lead to that. However, I actually have a problem where those kind of semantics may make sense, which is, we could call it like conjunctive semantics, which is something like only if you are authorized to R1 and R2, are you authorized to this permission P1. So there's a thing that I worked on Java, using RBAC in the context of authorization to Java methods, where I think that kind of semantics for roles makes sense. Unfortunately, the student graduated and we haven't done anything since then. So anyway, yeah.
You can only open the vaults.
Yes.
If there are two keys that open the
Yes,
vaults.
yes,
Yes.
yes. So the context there also is slightly different, which we can talk about offline, which relates to the default, like, the catch-all. We usually assume that the default is deny all, right? That's what we usually assume for firewalls and things like that, right? Now, if you want a default of allow all as opposed to deny all as well, then maybe for one of those options, I don't remember which one it is, then this one makes sense. I mean, we can talk about more detail that work.
But anyway.
But the bottom line is, bottom line is nobody has explored.
Equality is because of the max.
Yes.
Otherwise,
yes.
it's superfluous.
Yes, and with the customary semantics of roles, which is that you don't have this kind of you need two of them. If you have any of them, you get the permission. Then that makes sense without the maximum. Okay, so the point of this is, of course, that we get a more efficient algorithm. Okay, and CNF-SAT, I assume everybody knows what it is. So reduction to CNF-SAT. So just wanted to put the UAQ back up there. Now, reducing to CNF-SAT, I just want to point out that capturing some of these inputs is easy. So from the standpoint of the policy, for each role that's authorized to a permission, let's say for every role I introduce a Boolean variable, R, and for every permission P, I introduce a Boolean variable P. For each role that's authorized to P, I just introduce a clause of this form, and the meaning of the clause, of course, that if I activate R, then I activate P. For each permission that's assigned to all those roles, I introduce a clause of this form, right? Because to activate P, at least one of those roles has to be activated. For each permission that's in the lower bound set, I just introduce a clause, just that permission by itself, because it has to be activated. And this is the thing that we were talking about earlier, which is that any permission that is not in the upper bound set, I introduce a clause of this form. The only somewhat tricky part, so that's pretty easy. The only somewhat tricky part is these constraints and these integers that capture the optimization objectives, because we need to be able to count, right? We need to be able, in the constraint, remember that it's a two-tuple, a pair, where you have a set of roles and an integer t, and basically what we want to be able to say is at most t minus 1 roles are activated from that set of roles. So we want to kind of be able to count. So it turns out that there was a previous paper on this problem that did subset enumeration, which is of course not efficient. So what did we do? We looked to circuit SAT. So we first reduced to a Boolean circuit, and then we went to the Corman, Lyserson book, Roverstein book, textbook, to reduce circuit SAT to CNF SAT. They have an efficient reduction from circuit SAT to CNF SAT. I think it's linear time or something like that. Anyway, so basically we have building block circuits which are quite simple. So here's an example of one bit sum. What we call bit sum is we want to add a bit x to the string yn minus 1 to y0. We have a circuit for comparing two of these bit strings, whether the count 1 is less than or equal to count 2, max, min. So you can imagine that these circuits are pretty simple. So here's a simple example of bit sum, which is I'm adding x to y1, y0. Of course, the output might be 3 bits because I may have a carry bit, right? So it's pretty simple. All said and done, the cost of a reduction from UAQ to CNF SAT ends up being n squared log n. And the log, again, we expect because of this counting thing.
But in a nutshell there, in the previous bit sum, you're doing a cardinality
Yes.
check, right?
Yes.
And so there are many ways of doing the encodings of cardinality constraints.
Okay.
So they are the properties that they have with respect to propagation of the set solvers.
Okay. So I wonder if any is better than what we've done. Because I can't think of a way of doing it other than just counting.
Oh, so you can sort. So what we can do is, so you can build a sorting circuit that sorts the bits that are zeros first and then the bits that are one. Okay. And then the cardinality constraints is basically the indicator of where you go from 0 to 1.
Oh, I see.
And the size of the sorting circuit, and then there are different ways of doing sorting circuits. And
so this might actually make the SAT solver more efficient in practice.
Yeah, that's right. And if you encode these, the adder circuits, you could encode them with different orders of the bits as well, and you get different propagation.
Okay, so we didn't think that far.
So there are these.
But it seems to me like in the worst case, it's still going to be some log n kind of thing.
Yeah.
Right.
If you want to get the smallest possible.
Okay, so we did some empirical stuff. We just ran it. So we implemented this in zchaf. Why? Because some people say, well, that's an old solver. Well, the reason one of the previous papers on this used that. So we just wanted to do a comparison. So we implemented the CNF SAT thing, and we have the, we call it the fixed parameter polynomial. It's the one of the algorithms that I discussed where we assume a certain bounded thing. So anyway. Well, so you'll see. So they both perform pretty well. So here, what we do basically is that because we have so many inputs and we want to draw a two-dimensional graph, we vary one of the inputs and we hold everything else constant, and then we look at so you know, I have an earlier paper where I proposed a benchmark for RBAC, so we tried it on those benchmarks. So they seem to do pretty well. So here's one where we expect that kind of behavior, right? So this is completely expected because that FPP algorithm we know is exponential in the size of this thing.
Can you remind what was the FPP algorithm?
So it's basically, I think the one that's shown there is this one.
Oh, okay. So it's one of your algorithms that
Yes.
specialized.
Yes.
Okay.
So here's where it sort of starts taking off. So I mean, you know, so it tells you kind of where you should maybe use one approach as opposed to the other approach. Okay, so that's it for the first problem. It's 1108. So maybe so the second one has also to do with access enforcement. And the problem is the following, which is that we want to come up with a data structure for enforcement. So we have a bunch of current sessions. Now in the customary architecture for access enforcement, people talk about something called a policy protocol enforcement point or policy enforcement point. Okay, so we would like it to be time and space efficient, right, in practice, maybe. So here's a data structure, that's a candidate. It's called a Bloom filter. It was originally proposed for set membership checking. And the way it works is, so we want to encode a set A, which is a subset of a universe U. And so, you know, so we first encode the set A in this data structure. And then at runtime, we have queries. A query is a U in the universe, and we want the data structure to tell us whether it's an A or not. Of course, we have plenty of data structures to do this, binary search trees, hash tables, and things like that. Now, how does the Bloom filter work? Well, we pick some number of buckets, kind of like a hash table. I'll call them bits, M. And we pick some functions that I'll call hash functions. What is the meaning of a hash function? Well, each hash function, hi, maps elements of the universe to one of the indices, 0 to m minus 1. So this is how we encode the set A. In a Bloom filter, we start with all the bits as clear, and then if we want to insert A, we set the position h of I for every I. For every one of those k hash functions, we set the bit. So that's it. So that's the data structure. It's now ready to be queried. Now, if I want to check if some u in U is in A, what I do is I subject it to every one of these hashes, and I check if any of the bits is clear. If any of them is clear, then I know that that U is not in A, right? Okay, so what are the properties of this time efficiency properties of space efficiency properties? What is the query time? Well, it's the time of doing k hashes. Now, I could choose the k to be constant in the size of the set A. The space is the m bits, which is also could be chosen constant in A. So this seems magical because now I have this, I seem to have broken the time-space trade-off. But of course, nothing comes for free, and here's the trade-off, which is that if I pick some u in U that is not in A, and then I query for it, it's possible that all the bits are set to which it maps under the hash function, and then we have a false positive. But this error is one-sided, so it cannot happen if one of the bits is clear when I check. Right? Okay, so to use this for access enforcement, we cannot deal with the false positives because in access enforcement we typically expect a 100% correct answer. So we went to the Bloomier filter, which was proposed in one of those algorithms when you Stock or Fox in 2004. We have an adaptation of it. So one of the ideas behind the Bloomier filter is quite simple. You actually take the false positives and then you store them in another Bloom filter. So basically, if the first layer of Bloom filter says yes, this thing that you're looking for is in the set, well, it may be a false positive. I need to check whether it is. How do I do that? Well, I check in another Bloom filter. So basically, we end up with L layers of Bloom filters, right? Where the layer I encodes the set AI, and it has a potential set of false positives Pi. So in the first layer, we encode the set A, and the potential set of false positives is everything that's not in A. In the second layer, we take the actual false positives in the first layer, right? And then we encode it in the Bloom filter. But the potential set of false positives is actually the set A1, and then we switch back and forth. Well, you may never eliminate all the false positives using only Bloom filters, so in the end we assume that we maintain an explicit list of false positives. Now, empirically we showed that this data structure can be effective for access enforcement in some other work, so I won't talk about it. The one I want to talk about is the problem of constructing an instance of this data structure. So what are the inputs? Well, the inputs are the A and the P, which are for encoding access, basically the sessions. So we assume some syntax for that. Let's say a pair, which is session ID and permission. We have a set of hash functions, candidate set. So there are heuristics on how to choose these hash functions. Specifically, there's a paper in Communications with the ACM many years ago where he shows in practice that cryptographic hash functions like SHA-1 are good candidates. We have the maximum total bits, so this can be seen as an optimization objective because we want to minimize this. We want to minimize this as well, which is the bottom, the number of false positives that come out at the end. We may want to minimize this, which is the time, and the levels it's not an optimization objective, right? We don't care. Usually we don't care how many levels we use. Yeah.
For multi-layer Bloom filter, for every element you want to check whether it belongs to set or not, you need to let it pass all the layers.
Unless one of the layers says no, it's not.
Okay.
Yeah. So that would be the best case. The best case is one of the layers says no.
So will this approach be better than just increase the number of bits you flow?
I will show you. We have empirical evidence for that. The short answer is yes. Right. So the effectiveness of using multiple layers is a question, right? Like why don't you just use yeah. Okay, so the decision problem is you're given all these things, it's the existence. Does there exist an instance of the data structure? It's certainly decidable in exponential time, but it's unlikely to be in NP. This is a somewhat informal comment, and the reason I say that, of course, is that if you look at these inputs, these are integers, and in binary, for example, if you use, depending on your encoding, they can be encoded in log m bits. Okay, so if I change those slightly to uppercase, meaning that I pre-allocate the space for the bits, and I pre-allocate the space for the explicit list, then it's an NP. Then I get an upper bound that I like more. Or the fact that I get this upper bound I might as well deal with this version of the problem than the other one, because this is as practical as the other one, is the claim. So if you pre-allocate the space.
It's also much more realistic, because the list you have to represent when you realize the checker.
Yes.
You have to represent the list.
Yes. You're right. So you could argue that this is more realistic. Might as well get it. Okay. So this, kind of, assuming NP is not equal to EXP, this kind of dramatically changes the complexity. We do have a lower bound. It is NP hard. It's not hard to show. Now, one thing is that it remains NP hard even for the classical Bloom filter. So I don't know if anyone has shown this result for the classical Bloom filter. We do have a gap preserving reduction for set cover. So if you perceive the final set of false size of the set of false positives as an optimization objective, then there's a pretty straightforward reduction from set cover that's gap preserving, which means that we don't expect to efficiently approximate it in better than log n approximation ratio. So I'm just going to look at the reduction to CN of SAT. And again, we went to circuit SAT, Boolean circuits. Here, the building block circuits are much more complicated. So we have a bunch of building block circuits. I have this nice picture to show some of them. I don't know that I want to go over them. So the filter map is just saying that should this bit be set or not. And it's going to be set if the hash of this element is 1, right? But I need to OR it with all the other elements. So that's what that is. But then we also have a question as to, okay, in layer I, do I choose a certain hash function? Is a hash function even valid? Well, how do I determine whether it's valid? Well, it depends on the number of bits I choose for that layer, right? So basically we have the number of bits that are chosen for the layer and all the hash function, and then basically this kind of outputs whether a certain hash function is even a candidate for a certain layer from our master list of hash functions. So things like that. And then of course we have false positives. So this is a fairly complex bunch of circuits, but it's fairly efficient. So the cost of the reduction is quadratic. Okay, so let's look at some fun empirical results. So the first question, do we benefit from multiple levels? The claim is that this graph shows that the answer is yes. So what we do is, as the goodness criteria, we use the number of false positives. So this is E size, this is a vertical axis. And we have something called problem size here. So this is from our benchmark, that RBAC benchmark that I talked about. Now it turns out that if you use only one layer, then this is the graph that we get. But as you increase the number of layers, you start getting better and better performance.
I mean, for one layer and multi-layer, are you using the same number of bits in the Bloom filter?
Yes. So the total number of bits is the same.
Oh, total number is the same. Okay.
Right, because that is the space that I want to allocate.
Yeah, but potentially you increase the query cost.
Well, that's not obvious, but potentially yes. But that's not I won't necessarily say that yes. Just because we use more layers, we use more. No, that's not necessarily true. Right.
But now, you want to use Bloom filters to implement a fast hash.
Right, an access check.
Access check.
So you get an access request. I won't immediately say yes or no.
So if you use a pair of hash, like two-level hash tables, you also get low collision ratio.
So let's say we use perfect hashing. So with perfect hashing, I'm guaranteed constant time query. But in the worst case, the space is quadratic.
Right, but if you have two hash functions,
right?
So then you can get the hash collision ratio.
Right. So in perfect hashing, we do use two layers. Oh, okay.
Not perfect hashing, but you rearrange. You insert your elements according to two hash functions.
Oh, I see.
And that allows you to use very small buckets. So when you overflow in one bucket according to one of the hash functions, you will typically overflow to the other hash functions.
Okay.
Bucket, then work around. So that gives you a space-efficient hashing. I was wondering if this Bloom filter could, what's the trade-offs between using, say, the Bloom filter and using, say,
I don't. So if I understand you correctly, what you're saying is that for each hash function, we use a separate set of buckets. Is that correct? Not the same set. Because
we use shared sets of buckets.
oh, then that's exactly the Bloom filter. Right? Because in the Bloom filter, I use k hashes. So there is a mathematics behind, given the size of the set A that I want to encode, what is the optimal number of bits and hashes I should use in the expected case. In the expected case, because in the worst case it doesn't matter, right? Depending on your input, you may do badly no matter what. But anyway, I don't know if maybe we can talk about it because maybe I don't fully understand. Okay, so
I use Bloom filters as a just to filter out negatives, and
okay.
I call the expensive algorithm.
Right. Right.
So that's the typical way.
Right. Right.
But if you use Bloom filters for the expectation of getting perfect
yes.
Hashing,
yes.
It seems that then the trade-offs might be to use a two-way hash.
So the first thing is that if I use two hashes with a shared set of bits, to me it sounds exactly like a Bloom filter. Now I could use separate sets of bits, but that's exactly the layering thing that we're doing, right? That sounds like a two-layered thing, right? And the point is that, well, why two? Why not five? So here's another question. Does adding another level always help? And the answer is no. So again, here we're going with E size, not the query time as a goodness criteria. And basically, here we're adding levels. So if I have a one-level Bloom filter, then my E size is over here. If I go to a two-level Bloom filter, so those are problem sizes, right? So I'm sorry. So I need to go back. So for a certain problem size, if I use a one-level Bloom filter, then I have the E size as here. But if I go to two, then it dramatically improves the thing. But you notice that for certain other problem sizes, when I increase to 3, I get a worse performance than I had with 2. And this is not surprising because we do the switching thing, right? So really the fair comparison should be between 2 and 4 or 1 and 3. And in that case, then I can say that using 4 layers is at worst as bad as using 2 layers. And similarly for 3 and 1. Okay. But adding 1 level doesn't necessarily help. And finally, is there a cost with using more levels? The answer is yes. So there are 2 answers to this. One is a sort of a complexity theoretic view. The other is this kind of empirical view. So the empirical view, you can see here that if I use only 1-layer Bloom filter, then this is for our implementation, right? Our CNF SAT reduction plus mini SAT, or running time of mini SAT, which is a SAT solver that we used. You notice that I quickly sort of converge to the best I can get within so much time. But then if I go to 5 levels, and I wait only whatever this time is, 10 seconds, I still get a pretty bad Bloom filter, and it takes a while before I, get even this crossing point, right? So in some ways, this quantifies the cost of using more levels. It's going to take you longer to construct instances of this thing. So
to make sure I understand, so you run minisets to synthesize the filter?
Yes.
For a given set of levels, 1, 3, and 5?
Yes.
And if you give it a longer time limit, the better quality?
Yes. Okay. And the point is that if you use more levels, you have to wait longer, right? So for example, if my patience was less than 10 seconds and I was using 5 levels, I'm going to get a pretty crappy Bloom filter because my resultant E size, which is my goodness criteria, is pretty high. Well, if only I had been, but the point is that in that case, I would have been better off using a one level, just a classical Bloom filter, because it would have given me a better E size if I was only 10 seconds of patient. On the other hand, if I was willing to wait 20 seconds, then I can have a 5-layer Bloom filter, right? Because then it's going to give me much better, because the one guy is now going to give me much better the level
So
one.
input to Miniset is the domain A and U. So A and U are enumerated, A and P.
So we move all these. So you have these possible, the A is the all,
U is implicit. Okay, so A.
no, use A union P.
Okay.
So A is the authorizations that are allowed.
Yes.
A union P is all possible access requests that I could get.
Okay.
Now you have to assume some certain things about the domain for this. Hey, Marco. And H is a set of all possible hash functions.
Right.
I mean, obviously we have to finitize this, otherwise it doesn't make sense for us to consider the computational complexity, right? And, right. M and E are like the space optimization objectives. K is the time, it's the query time, because I'm allowed to use at most K hash functions. And the L is really, we don't care, but we put it in as a, oh, by the way, so just because Marco came in, this paper is his paper. I'm not talking about it because we did some more work on it. Anyway, okay, so yeah, so that's the input. Okay, so yeah, so I think the empirical results is somewhat interesting. Right? We still have one kind of open problem here because we did look at it from the standpoint of this fixed parameter thing. And on one of them, which is the most interesting case, I would say, which is, do the number of levels lend to intractability? That question we have not answered yet. So we have the empirical answer, but we don't have the computational complexity answer. Time's now 11:27. Okay. Now we come to Karthick's work, which is policy verification. So here, this part, if you remember, is the delegation from the super user to the semi-trusted admin who's going to make changes to the authorization policy. So here, I have to introduce some new syntax. I generally don't propose policy languages. So the first question we have to consider is, okay, what is a meaningful language for delegating things in this context? So remember that the RBAC policy consists of, we could think of it as consisting of 3 pieces: the authorizations that users have to roles, the relationship between roles, which I don't show here, and the relationship of roles to permissions, right? So the question is, what should a delegation model look like to administer something like this? And there's quite a famous proposal in the community from 1997 called ARBAC. We're going to focus only on the user role authorization part. And there's good motivation for that because it's been argued that that is the one that changes the most in enterprises. So here's their specification of a language for doing this. Okay, there are 2 things that you can do. You can assign a user to a role, or you can revoke a user from a role. Accordingly, we have 2 sets of rules that they call can assign and can revoke rules. Each entry in the can assign set is a 3 tuple. It looks like this. We define something called an administrative role, and we give, we put members in it like Alice, Bob, and things like that. And we say that this administrative role is allowed to assign users to this role. Members of this administrative role are allowed to assign users to this target role. So for example, we might put Alice as a member of A, which means that she's authorized to assign anyone to be a member of RT. Now the only additional thing is that we constrain her by putting a precondition. So basically we don't want her to have unfettered authorization to assign users to RT. So what does the C look like? So here I'll do it by example. The C is a sort of a propositional kind of expression on existing role memberships of the user that she's trying to assign. So let's say that Alice says, okay, I want to assign Bob to be a member of engineer, well, she's constrained. Bob has to already be an employee, member of employee, and he should not already be a manager. If Bob violates that, she cannot do that. Right? So that is how the super user gives control delegation, because presumably the super user wants to control how these sub-administrators are allowed. Okay, what about revocation? Well, it looks similar, but without the precondition. So all we're saying here is a member of A, for example, Alice is allowed to revoke users. So if, for example, Bob is a member of employee, then she can just say, oh, he's no longer a member of employee. Now, the question is, why is there an asymmetry? Why don't we have a precondition here? And the rationale stated is that the monotonicity assumption, which is that revocation is an inherently safe operation. You're only going to take away privileges, not give privileges. That is the rationale for that. So you can imagine the assumption here is that all the permissions are positive permissions. There are no negative permissions. Okay. So safety, the question is, of course, whether a user could acquire membership to some role by some sequence of actions. So more precisely, if I was to write it as a language, we have a start state, which is the RBAC graph, right? We have these rules, right, by which the state can change. Okay, I'll explain this in a second, the trusted users, and then we have a query. Okay, what is this set T of trusted users? Well, so that comes up from, it doesn't change the computational complexity or anything, but it comes up from practical considerations, which is that, let's say the super user trusts Alice, but he does not trust Bob. So what he's going to do is, and Alice and Bob are administrators. They are the partially trusted admins. What he's going to do is he's going to put Alice in this trusted set. And the meaning is that she's not allowed to do anything as part of this analysis. She's not allowed to assign any users. She's not allowed to revoke any users. So it is a very coarse-grained way of trying to capture insider abuse. Because I trust you, but not him. So I'm going to put you in the trusted set and assume for the purpose of analysis that you don't do anything. Now you could say that this is very coarse-grained because you should be allowed to do some things because, and things like that, but that is the way this problem we have set it up. Okay. So the intent there is to capture some kind of insider abuse thing. So in some earlier work that I did that was published in 2008, we showed that this thing is p-space complete, and I just wanted to put the relationship of the complexity class here. Now, one of the comments here is that when people design these things, they don't think of policy verification, and that's the point I'm trying to make here, that it is a limiting factor for adoption of this, because you can't even give a tool, for doing this kind of basic policy verification. Okay. Model checking is complete for p-space. Why don't we try it? So Karthik tried it on some benchmark policies, and you can see for even kind of relatively small policies, he was getting poor performance on his desktop PC. So of course we have to use some tricks. So what did we do? We complemented it with abstraction refinement and bound estimation, and then we used bounded model checking. So these are domain-specific tweaks, right? So abstraction is transformed into a smaller problem, ensure one-sided error, specifically that if the smaller problem is unsafe, then so is the original. But if the smaller one is safe, then we basically have to refine, meaning increase the throw more things in. So of course it's highly effective if safety is, the unsafety is shallow. So where Vijay came in is that he was like, well, coming from the bug finding kind of mindset, which is that if you think of unsafety as a bug and you make the premise that software people, I guess, do in testing, that bugs are easy to find, right? We don't know if these are validated in practice for these kind of policies. Okay, so that's of course how it works. Generate the initial abstraction, model check. If it's unsafe, then we're done. If it's not, then we have to refine till eventually we go to the thing. And the bound estimation, how does that work? Well, we have a state reachability graph, and what we want to do is hint the model checker with an upper bound on its diameter. The diameter is, of course, the length of the longest, shortest path between any two nodes, because we know that the model checker does not have to go in cycles. Okay, so Karthik implemented this in a tool that he calls Mohawk, which is downloadable. By the way, the other things that I presented are also downloadable. I think the CBF one, we're still working on it. I'm not sure if I put it out there yet, but all the code is available for download. Right, so we're going to take the policy and the safety query. We're going to do some mundane transformation. We're going to do the abstraction. So we have the abstract policy. We're going to estimate a bound on it, and then we're going to invoke NuSMV. If we get on safety, which we call an error, then we're done. Right? Otherwise, we're going to refine. We're going to do estimate a new bound, and then we're going to invoke NuSMV again. So here's Karthick's approach to abstraction refinement, which happened to work for the benchmark policies. So what he does is he does something somewhat straightforward, which is he defines a relationship called related by assignment between roles. So for example, if you have AC R1 in can assign, and if there is a precondition role R2, then we say that R2 is related to R1, right? And then he builds a tree based on this. So here's a simple example where you have those can assign rules. So you notice, for example, that finance is a precondition role for budget committee. So he basically puts an edge like that, right? But budget committee is on top because that is the target role, right? Similarly, if you look at finance as a target role, then you have accounting and audit over here. So he puts them here. And if we have a query like could Bob become a member of budget committee? Okay, so basically what we're going to do is we're going to prune the policy, and we only take that part of the policy that refers to some constant number of roles by this priority. So you could have that Ka to be 1, which means we'll start off with only, I think we start here, right? Okay. Oh, we start at the top, okay. So we will actually throw away all of these guys. Actually, we'll throw away everything. Right, because even the finance role is not in there.
So the abstraction is under approximation.
Yes. So okay, so of course the refinement is you throw in KR more roles, and they're tunable knobs. They define how aggressive we are.
So it's basically a slicing. So as you create some slice of the system,
right?
Increase the
yes. Okay, bound estimation. What we're looking for is an upper bound of the diameter of the state reachability graph. Of course, we would ideally like it to be tight. Now, if I have R roles, R is a set of all roles that appear on the problem instance, then I immediately have an upper bound like this. So why is it that I have a -1 in the exponent here and the +1 here? Well, the reason is that the role that's in the safety query, we know that the only thing we have to do is assign a user to it, and then we're done, right? So there's only one state transition that applies to that guy. That's why it disappears from here and goes here. And that already gives a hint about as to how we do the bound estimation. Now, of course, there's a question, how tight is the bound? And that relates to some foundational question in computing, right? So we don't expect a tight bound unless P space equals EXP. And we don't expect to answer that question as part of this work. Okay, so what is our strategy? We progressively remove terms from the exponent, which is up here. They don't disappear. They're likely going to get added over here. Right? So here's a simple example. We call these various approaches tightenings. So let's say we have the safety query that refers to the user U and the role R. We identify those rules, A1 through AK, in the can assign set, whose target role is R, which is the safety one. And then we we identify sets of roles that may cause each of those to fire, right? And then we pick the largest size subset among that one, and we can replace the set of roles that we started with, which is from the policy, with this one. Why? Well, basically, we know that one of them fires and causes the user to become a member of R. That's it. And we need at most one. So similarly, we have various tightenings. If there's some preconditions that appear negated only, then we know that the only thing that can be done is revocation from those roles, right? So basically, we end up with a set of roles here that we can remove from this, and then we stick them here. Right? And we don't sacrifice any correctness. That's what the theorem states. And now we get a dramatic improvement. So this is the final result on our benchmark. This RBAC path thing is a prior work that was done at Stony Brook, where they have a, I don't know if it's publicly available or they emailed you the code, right? Okay. So Karthik asked for it and they emailed it to him. So of course, I'm only presenting the good news for our tool, which is that in the paper we talk about what the trade-offs are. Right? That classification of the test suites with the complexity comes from the fact that if you remove certain syntactic elements from the problem, then you end up with a problem that's in P or NP complete and things like that. Okay. Oh, right. Very important slide. My university hired a. It's my final slide. I think Marco might like it, especially because he's a UW grad. University of Waterloo, I should say, because there is a UW here, right? Right. So Waterloo had this kind of a traditional academic-looking insignia or whatever it is. And they hired someone, and he or she proposed this new fancy logo for the university, which some people say is more appropriate to a disco club than a serious university, but oh well. Maybe it's the other universities that are behind the times. I think they have quietly gone back to that one. I think that person left the university, and now I noticed that, anyway, whatever. Oh, really?
High-end bars.
Oh, okay. So
This will be for fun events, this will be for just official.
Oh, right. Well, there was a time that they said that if you wanted business cards as faculty, I mean, I don't print business cards anyway, but they said that no, we cannot give you with that one. You have to take the new one, right? So people were saving their old business cards because they didn't want the new one. But now quietly it turns out that you can, somebody told me that now you can order with the old one. So I think they're quietly kind of moving back without. Anyway, thank you for your time and the opportunity.